and thanks everyone for joining today's webinar. As you can see on the screen, and you probably know, that's the second part of a two-parts webinar on solid structure interaction applied for integral bridges using Midas Civil and Midas GTS. So in this second part, what we are looking is at two more applied examples on how to model integral bridges and take into account solid structure interaction. So I think we can make a start. So the agenda for today is short and nice. We'll start with an introduction, very quick one, and then we will jump to the first example, which is an integral bridge on piled bank seats. And then we will continue with another example, which is another integral bridge, but now with full height abutments and supported on a single row of piles. Before we start with these two examples, as I said, this is the second part of a two-part webinar. The first one was more focused on the theoretical background and the different analysis methods that are available. So just as a refresher, we covered the limit equilibrium method. We covered the spring analogy, and we talked about linear springs, so the method of subgrade reaction, and we covered PY curves or nonlinear springs as well. And we talked a little bit about the continuum media approach. And then we revised the requirements on the PD 6694. What we are going to do today is try to take all these things that we discussed and apply it to different examples. So the first one is this one that is shown on the screen right now. That's an integral bridge to span over a river. It's on a not very competent soil. It's kind of soft clay. And then we have decided to build this bridge in a top-down construction. So we're gonna excavate this clay. We are gonna build the top part of the bridge, so these abutment walls and the deck. Then after we do that, we are gonna backfill the abutments with a granular material, cohesionless material, backfill class 6N. And this bridge will be supported on piles that go all this layer down to a competent layer. So they are 22 meters deep. When we have this integral bridge, probably the first question that we will have is, okay, what should I do to take into account solid structure interaction, to take into account the racketing effects on the behind the abutment wall? Well, if we are looking at the PD 6694, basically, so I was discussed on part one, we have two different main approaches. The first one is limit equilibrium method, and that can be applicable when we can identify, without doing any solid structure interaction, which is going to be the movement affecting the soil. And if we cannot identify this movement, or thermal movement is quite significant, more than 40 millimeters, or is a skew bridge, and or situations, then we need to run a solid structure interaction. If I go back to our example, we can see that the top part of the abutment, the abutment wall is in contact with a granular soil, so we'll have racketing effects in this area here. However, the piles, they're embedded on a clay material, a cohesive material, and according to the PDC 694, we can neglect the racketing effects. So all the piles, they will not have any problems with racketing effects, but it's going to be only the abutment wall. Since we have a very shallow abutment wall, our assumption is going to be that we can identify the movement of this wall. We're going to assume that this is mainly transactional, the kind of movement that we can expect from this top part of the bridge. So if we do that, then we can go to this clause on the PD 1694, which says that for thermal movements of accommodated by translation without rotation, we can use certain formulas. Okay, so now we have a formula to use for the soil pressure. Then we can start looking at the soil properties that we have to use. So we have said that this is a class 6 N backfill. We're going to assume a 20 kilonewtons per cubic meter density and an internal friction angle of 35 degrees. And then we need to understand what are the lateral earth coefficients. And the lateral earth coefficients, we don't have just a single one, but depends on the situation, if it's contraction or if it's expansion. And as well, we have some variation along the surface life of our structure. It will start for something, a lower bound for expansion, for instance, of K0 min. And when the soil racketing effects and the large number of cycles starts to pile up, this coefficient will increase to an upper bound that's going to be the K star. On the contraction, we have some range of values to take into account as well, between K min and K naught max. Then straightforward from the soil properties, we are able to calculate the coefficients for the three of them, the K0 min, K min, and K0 max. However, case that does not only depend on the soil properties, but as well depends on the movement of your bridge, because this is the range of the movements that you can expect from the seasonal loads. The thermal loads is the one that's going to define the value for this case stat. So our first task would be assess the magnitude of these movements. To do that, we're going to start working on Midas. Since we are covering two examples today, I have started with a model that it has been already prepared to a certain level. So we have the model representing our bridge here, the way that we decided to model this bridge, which is basically shell elements for the deck, because we are assuming that the deck is going to be a concrete solid slab. Shell elements for the abutments as well, 1 meter thick, and then for the piles we have beam elements representing that. So first mission for us with this model is we want to understand what is the movement that we can expect. So we have the piles at the moment, but what we don't have on this model is the stiffness of the ground around the piles, and that may be very important identifying these movements, because if the soil is very stiff, it's going to prevent the deck to expand, and then we will have a smaller value for the expansion and the contraction, and then we'll have a value for the K star. If it's a very soft soil, then it's going to allow the deck to expand and contract a bigger magnitude of movement, and then we'll have another K star. So getting the soil stiffness around the piles properly, it's very important. As discussed on part one, we have different methods of doing that. If we want to use the spring analogy, I'm going to explain the two of them using Midas, but obviously we are going to use just one of them because we have to make a decision on our modeling strategy. So I'm going to start assuming that we want to use PY curves for modeling the spring stiffnesses on these piles. I'm going to use my own PY curves that I've found on some literature on tests on similar grounds as the one that I'm building this bridge. And I want to replicate exactly these PY curves in Midas. If I want to do that, I'm going to go to the tab boundary. I'm going to go to this point spring menu here, and then I'm going to click first on forces deformations function. And this forces deformation functions basically allows me to define any arbitrary relation between the displacement on a spring and the reaction that we are getting. So for instance, I'm going to say that this is a PY curve for a specific depth, 1 meter from the surface. And then I can write here just any arbitrary function that I want to impute. So for different displacements, I'm gonna assume different values. and this creates our PY curve. That works same way for compression or traction or reactions on one direction or on the other direction. If I create this formula, this function, I can save it by clicking apply, and what probably happens is our PY curve depends on the depth. So maybe need to create another one for 2 meters deep, which has different values, and I can save it as well. And this for as many depths, as many points I have on my piles, I need to create one of these functions. So we have one for z equal to 1 meter, another one for z equal to 2 meters now. Okay, when we have these functions, then we can go back to the point spring menu, and now clicking on point spring, we can select the piles that we want to apply the springs. Just for making it simple, and so I just select one of them. Apologies, just one. Just want to select one node, the one that I want to apply the spring. And then for this menu, we don't want a linear spring. We want PY curve, which is a nonlinear spring. And this is by choosing the option multilinear on type. And when we do that, we will get a drop-down menu here with the functions that we have created previously. One for z equal to 1 meter, another one for z equal to 2 meters. So I can choose whatever function I want, the direction that this is being implemented, and then clicking apply. And I will get an sign like this one showing in yellow that's a spring, and the first of these elements here means that's on X direction. Then I can do that for every pile and every level, and I will be creating my nonlinear springs for the model. However, that can be a little bit tedious because that will mean manually inserting all these different springs to all the different nodes that I have in the model. However, we have another option for doing that. So I'm not going to use this approach right now. I'm going to use another approach that's built in PY curves that Midas offers for you. And you can access that going to integral bridge. And then when you have selected integral bridge, instead of abutment spring, you can select pile spring. And then on this menu here, you have 3 different PY curves, one for sand, one for soft clay, and another one for stiff clay. And then with these definitions, defining the ground level, the pile diameter, that we have 750 mil diameter piles, density of the soil, and a number of different parameters, we can just apply that directly to all our springs, and Midas automatically will calculate the different depths of the nodes, and depending on the coordinates of the nodes, we will implement the relevant PY curve. We do that, then we have all these nonlinear springs at the different levels. The only limitation is these PY curves, you have just 3 of them that have been built in, and maybe your site conditions or the kind of analysis that you want to do is not exactly the PY curve that you want to use. Then you are limited to the 3 ones that have been implemented on Midas. But that's there for you to use whenever it's convenient. Okay, that's not the method that we're going to use either. We're going to use the method of subgrade reaction for this example. And this is done in a different way. If you go to the surface spring menu here on Midas, then select distributed spring that you apply to a frame element with a width of 750 mil. And I'm going to assume that we have a modulus of subgrade reaction of 10,000 kilonewtons per cubic meter. If we do that, we select our piles, and we apply. Then we will have a symbol like this one on Midas that means that we have implemented this distributed spring on the frames. And then what Midas does is basically when it finds that a frame has this distributed spring, calculates automatically which is the equivalent point spring on the nearest point of the frame. So it prevents you to doing this manual calculation. Okay, now these are the ones that we're going to use for this example: the linear springs, the method of subgrade reaction. The next thing that we need to input in our model is the temperature loads. In order to do that, we're going to the load tab. We are going to select our deck, making sure that we have selected all the elements on the deck. And then on the load tab, you have to select it within these options, the temperature per stress loads, and then you have an option element temperature. If you select this one, you will be able to assign expansion, which I labeled as T+, and that's going to be 30 degrees expansion. And then selecting the same elements by clicking this button here, select previous. I can do the same with minus 30 degrees for contraction, or T- in my load definitions. Right. Now we have the stiffness of the piles properly modeled. We have the temperature loads on our deck. So we are in a position to run our analysis. We have run our analysis, then we can check the deformations, because basically that's what we were after. And for instance, for expansion, just the displacement in X direction, and we activate the legend to see the values. We see that basically this expansion contracts 3 millimeters. So this is expansion 3 millimeters here, but we check T-, we'll see that this contracts 3 millimeters as well. Which, if you do the hand counts, that's basically almost the same as allowing the deck to expand freely. Which, well, it's kind of expected, because we have kind of slender piles that is going through a soft layer, so they are not really changing much the behavior of the deck. Okay, that's good. If we have these values for the expansion and contraction, then we should be able to get our K-star. So we were using PD6694, clause 943. And then says the K-star can be found using this formula here. And this this is the expansion of the deck. It can be found using the characteristic expansion, that's a thermal movement. That's the one that I just found on Midas, and using these partial factors here. If we calculate all these values, we finally get a K-star of 3. Yeah, we're getting with the K-star of 3, then we are able to calculate basically the earth pressure on the back of the abutment for all the 4 different situations, and all the envelope of earth pressures that is occurring on our bridge. Knowing that, we can go now to the model again, and we can start inputting these values. So I'm going to do that now. So basically, what I'm going to do is select just the abutment elements, these ones here, these ones here. I'm going to go to loads. In this case, we're going to select static loads, and we are going to select the hydrostatic pressure, because it's more convenient for us to define these variable loads in Z. Okay, let's start with K-star. We're going to insert the load case K-star. This is applied to plate elements, that's correct. And then the reference level is 0, because the ground level is at 0 in our model. And then this gradient intensity basically defines every meter how much increases our air pressure. So in our case, our K-star was 3, and our density is 20. So the gradient intensity is 60 kilonewtons per cubic meter. Per cubic meter. If we do that, well, that's happening on the opposite direction as expected. We can just change the sign. select again. Okay, and now it's fine. So that's a kind of pressure profile that we want to see on our abutments. Then this is for K-star. We can do the same thing for K0 min. In this case, instead of -60, that's going to be -8.6. In K0 min, it's going to be, select the same elements again, it's going to be -5.8. And we do the same for the last load case, which is K-min. And in this case, that should be 3. Okay, now we can double check. We had 120 kiloliters per square meter at the bottom of the abutment, which is basically the one that we said that it should be there. Same for the K0 max, K0 min, and finally the K-min. So we had all the earth pressures here. So that's fine. Now we can run the analysis again. And now we have our results. We have the thermal load applied, and as well the different earth pressures that are being applied. In this case, since I've used linear springs, I can calculate all these different effects as individual load cases, and I can combine them later. If we are using PY curves, we should be analyzing temperature and the reaction of the piles and the earth pressures all on a single nonlinear case, but in this case we can use superposition. And then the only thing I want to demonstrate now is depending on the situation, we will have more onerous effects on the piles. So for the deck, having a K-star, a really big pressure on the abutment, is going to give us a lot of compression. For the piles, it works on a different way. So let's do the combinations first. So what I want to combine is, first I'm going to say expansion plus K star. So we have expansion, K star. Another one that is again expansion, but K0 min. And now contraction with K0 max. And contraction on K0 min. K min, apologies. K min. That's the last. That's the last combination. Right. So for instance, for expansion, if we are checking the depending on the piles, if you are using the upper bound for the earth pressure on the abutment, I'm gonna just select the piles. Okay, that's good. We're getting these values here. But if we are using K0 min, we are getting much greater values. So for the case of the piles, K star is not unfavorable. Actually, it's favorable for the expansion case. So we should be making sure that when we are analyzing our bridge, we are taking into account not just the K star when we have the highest pressures on the backfill, but all the upper and lower bound depending on the element that we are designing. So when we have this graph here, usually this one is going to give you the maximum compression and hogging moments on your deck, but this one is going to give you the worst bending in your piles in this particular bridge. If we check that on the contraction case, we will find out that the worst case scenario is when we have K0 max applied. So we really need to check the envelope of these different values when assessing the earth pressures. So that's what I wanted to cover on this example. So it's a relatively simple example where you can use the limited equilibrium method when assessing the earth pressures on the back of the abutment wall. Now I'm gonna jump to another example, which is a little bit more complex, which is this one shown on the screen. So in this case, we have a full height abutment wall, 7 meters high, much higher than the previous case. We have a granular material on the backfill class S6N. Just for simplicity, I'm assuming that that's a constant thickness layer. Obviously, in reality, that's going to look something like that. But for our analysis, I'm gonna ignore that. And this structure is supported on a clay stratum, and then the piles reach a competent stratum beneath this clay stratum where the piles are supported. So again, we don't need to take into account bracketing effects on the clay layer, but we need to understand what are the additional stresses, the stress profile due to soil bracketing on this granular material here, on this backfill class 6N. And how we do that? Well, if we check the PD 1694 again, it says that we need to go to a solid structure interaction model because we cannot easily identify what is going to be the movement. So that's going to deflect, but we don't know for sure which is going to be the depth affected by this movement. So it's difficult to assess the stresses. It's something shown as well on this figure here. And then when that happens, we need to run a full solid structure interaction analysis. And what I'm going to do is use the method explained on the PD 1694 Annex A, which is an iterative process when first you define a starting point for this expansion of the deck. With this value, you assume initial values for the D and for the H. You use these values to derive soil properties. And when you have derived the soil properties, you apply a contraction first, half of all the thermal movement, and then an expansion for the whole thermal movement. And then you identify the depth where the horizontal stresses are equivalent to the at-rest pressures. Then, knowing that, you will be able to extract what is your new H and D, and you're going to compare these values with the ones that you used to derive the soil properties in step 3. They're very similar, then you are done. But if they are not, you will need to run another iteration. Right. So what are the values for our soil properties? Well, we know what is our expansion, free expansion initially. For the deck, we're going to assume that it's the free expansion of the deck without any restriction. From that, we are going to be able to calculate the D prima. That's the movement at half depth of the abutment wall. And with that, we are able to calculate the soil properties at different depths. And these values here, I'm showing you the whole calculation, but basically what you're after is this Young modulus, which increases with the depth. And it doesn't increase linearly, it increases slightly exponentially. Right. Obviously, these values depend on the value D prima, which has given us this factor here, which basically determines the value of the elastic modulus. but we don't know for sure that's the value that we were going to get from our model. So we are going to check that by building up a model that looks like that. So in this case, I'm going to keep it very simple, just for the purposes of this webinar, but obviously that can be more complex. We are going to work in a 2D model with a 1 meter strip, when we are going to model the half of the deck and the abutment at the abutment wall, and then we will have the pile. These elements, the structural elements, we are going to model that first on Midas Civil. And then we are going to use Midas GTS to model the terrain around our structure. Since we are checking now only expansion and contraction, we are going to use symmetry. So we are going to just model half of the ground and half of the bridge. Just with expansion and contraction, you can do that. But for other more complex cases, or when you want to start taking into account, for instance, braking and acceleration or unbalanced loads on one side and another, then you will need to model the whole bridge. Right. So we said that the clay material doesn't need to take into account racketing effects. So we're going to model that just basically with the solid properties that we get from the GI or whatever information we have available. For the backfill, this one is affected by the solid racketing effects. And as we have seen before, the elastic modulus varies with the depth. So what we are going to model is a series of strips, horizontal strips, and every one of these strips will have a variable Young modulus. But all the properties will, other properties will be the same. The internal friction angle, the cohesion, density, and the Poisson ratio is going to be kept constant, and we're going to vary the Young modulus with the depth. In this case, we're going to use a more Coulomb ground model. You might consider using another kind of ground model if relevant, but just to keep things simple, we're going to use a more Coulomb nonlinear model, which basically it means that it's going to not going to behave elastically, but where the stresses on the three directions go beyond the Coulomb yield surface, then your ground will start acting plastically. That's why we need these properties as well. The internal friction angle and the cohesion for both the backfill and for our clay. All right. So now we are ready to start with this example. So what I'm going to do is start a new model in Midas Civil, because I'm going to start modeling the structure. We can start with a blank model. And the first thing we are going to do is go to structure and structure type. And since we are modeling just a 1 meter strip, we're going to do a 2D problem. We are going to choose an XY plane. The reason we are using an XY plane and not an XZ plane or another plane is because then Midas GTS, when I'm using Midas GTS, that's the kind of plane that it uses for 2D analysis. So we'll select the XY plane. Then we have a model that is restricted to the XY plane. And I start creating my elements. So go to the tab, node element. I create a node at 0, 0, 0. So that's the first node in my model. Then what I want to create is the deck. So I'm going to use the command extrude. I'm going to extrude one node to be converted to a line element. And since the span of the bridge is 30 meters, and we are modeling just half of it, I'm going to extrude 15 meters this node. So I select the node that I just created, I extrude by 15 meters, and then I have this beam element here. It doesn't have properties yet, we're going to do that later, but first we are going to define the geometry. Now what we need to do is define the abutment wall and the pile. The combined height for these two elements is 20 meters. So now I'm going to extrude this node that just created here. and I'm going to create segments of half a meter because I want this to be split in half a meter beam elements to then have the mesh surrounding the material with the ground properties properly attached to it. So we're gonna make that by 40 meters. So 40 times half a meter, that's 20 meters. That's the depth of the bridge. And just we need to make sure that this is on this is negative. Okay. Right. Okay. So we have the geometry now on Midas. The next thing that we need to do is assign properties. So I'm going to go to the Properties tab, Material Properties. I'm going to create a concrete material. So I'm going to select concrete, and I'm going to make it, again, simple. Assume everything is C40. And then we have the material. Next to the material, we have to create section properties for this beam element which I have just created. So I'm going to go to Section Properties, Add. And then here, I'm going to assume that the deck is a rectangle. So I'm going to make it a rectangle, 1.5 meter deep and 1 meter wide because we're modeling a 1 meter strip of our structure. We select user to be able to input arbitrary values here, and using 1.5 meter height, 1 meter width for the section. That's the deck. We are going to create the abutment wall, which is 1 meter thick. So I'm going to change that to 1 meter. And then I'm going to create the pile as well. So the piles are 750 mil diameter. So I change the section tab to solid round, and then I just use 750 millimeters here, or 0.75 meters. Now we have the 3 sections to use in our model. We can just go and assign that by selecting the element. And then one thing that we can do is going to works and just dragging and dropping the different sections that was here. And then we need to understand in which point this is a abutment wall and which point is a pile. So that happens at this node here. So we're going to select all the beam elements below this point. They're going to be pile 750, and all these sections here, they're going to be our 1 by 1 section. Now probably you have noticed that the abutment wall and the deck, they seem to be the same thickness. And that's because we are working on an XY plane. Midas by default understands that when you're using depth of section, it goes on Z direction. So if we change the view, you will see that the 1.5 has gone through the wrong dimensions. We want to keep the 1 meter as width and the 1.5 as depth. So one thing that we can do is just select this element, go to node element, change parameters, and then element local axis, we just turn it by 90 degrees. Alternatively, you could define the section instead of 1.5 times 1, making it as 1 by 1.5. But it's a good excuse to show you how to change this angle as well. Right, so that's everything I want to model in Midas. Again, I know that's a very simple example, but the same principles apply to a very complex one. A 3D example will be the same process I'm explaining here. So when you have all your structural elements in Midas model, the next thing you do is you go to File, Export, and export MXT file for FEA GTS. And that's just a change format that allows the program to share files with the different softwares. So we create this file, and then we will see something like that. A text file which contains all the information from our model. The nodes with the coordinates, the beam elements, the materials, etc. And this is a format that Midas GTS can read. And another important point is you can create that with Midas, but you then can manipulate that easily with any text editor, or you can create from scratch with any text editor. So that gives you a lot of power when creating models. And that works both for Midas Civil and Midas GTS. Now that we have our exported file, we can go to Midas GTS and we can start our model. So we create a model from scratch. And then the first thing that's going to ask you Midas GTS is which kind of model do you want to create. And then, as I said, we want to create a 2D model. But the same principle works with a 3D model. But just to keep things simple, we're going to make a 2D. And by default, Midas GTS assumes that the gravity direction in 2D models is in y direction. That's why we wanted on Midas Civil to create everything on the XY plane to be consistent between the two softwares. If we do that, we'll get basically a blank file that we can start working. The first thing that we're going to do is just go to this button here, the Midas GTS button, and we are going to import the file that we just have created. So we go to Midas MXT and basically open this file here. And then you will see that the beam elements created on Midas Civil have been inserted on Midas GTS. Now we are going to work, we want to work on this plane here, the XY, because the Y is on the gravity direction. And another thing that we need to do is change the working plan to the same plan that we are viewing here on the window. So we're going to select this plan here, making sure that the working plan, this working grid, is aligned with our model. Now the next thing to do is modeling the soil surrounding our structure. First, and this is done first creating a geometry, which is basically CAD information. It doesn't have mesh information or properties or materials, but it's basically just defining the geometry. And so we can create this rectangle that goes, for instance, from this point to basically here. That's the ground level. We are going to do the same on this side, and then we are selecting an arbitrary value for the length of this element. Basically, you want to make sure that this is wide enough so the results we're getting at this edge they're not influenced with local effects of the structure. So we are making an assumption that 50 meters is enough. If on the results we are seeing that there's too many local effects here still, maybe we need to increase the width of this element. And we do the final one. From this point to this point. Okay, as I said, that's just the geometry. Now, from this geometry, we need to create the mesh to assign the properties. To create the mesh, we go to the Mesh tab, and we use the 2D mesh. We select the objects that we just created. We are going to use mesh size of 0.5, consistent with the size that we have used on Midas Civil. And for now, we are not going to assign any properties. We're going to define that later. But I'm going to make sure that that has a name that I can clearly identify later. So that's the clay layer of the ground. I'll click on apply, and then that's the backfill. 0.5 again for the mesh size, and I click on apply. Right. So now we have our mesh created. What we are missing is the properties of this ground on the mesh. So what we are going to do is, if you remember, we already had which were the soil properties. So basically is apologies. Yeah, we have this 35 degrees friction angle and the equation for this one, same for the clay, and then the variable Young modulus for the backfill. And these values were calculated here already. So what I'm going to do is, well, I have created an Excel file with all the properties that I want. I'm just going to import this Excel file. So I'm going to import this Excel file, which is automatically going to create all the different properties, and that's for every strip of the backfill. You will be able to see that has the elastic models that we have just calculated. It's a more column model, and it's nonlinear with no cohesion and 35 degrees internal friction angle. And then all the different backfill elements are the same with changing elastic modulus. Now we have all the materials. The only thing that we need to do is create properties, one property for each material, and then we are going to assign that to the mesh. What I'm going to do, due to time constraints, is just not doing that live, but just going to another version of the model where we have all these already assigned. So I'm just now showing you that we have the backfill that is represented by different materials at every half a meter, and then all of this is the there's the clay material. So next thing that we need to do, apologies, I'm just removing that because that's exactly what the next step that we're going to do. I'm going to add the constraints to the model, which we don't have any constraints at the moment. To do that, we go to static slope analysis, constraints, and then the first one we are going to apply is one called auto. That is going to identify the bounding box for our model and apply the conventional boundary conditions. This is basically no horizontal movement on the vertical faces and fixed on the bottom face, which is good. But since we are using symmetry on the left side, I wanna add that as well. So we have symmetry along the IZ plane, which is basically no movement on X, but I want to prevent rotation as well. We're going to select the symmetry plane IZ, select these nodes here, and apply that as well. So you will see some blue symbols that says to let you know that rotation is prevented here. So that's symmetry boundary conditions. Next thing that we want to do is add the different loads. So basically, they have been assigned already, but just to show you how they look like, we have gravity, and then element temperature on the deck. I have applied 30 degrees contraction, and then the full range of expansion, this is 60 degrees. And that's represented by this symbol here. And yeah, basically 30 degrees contraction, and then 60 degrees expansion. The next thing that we need to do is setting up the stages. So we go to stage set. We create one stage set with a random name, and we're going to tell the program how this thing evolves on time. So the first stage is going to be just existing ground conditions to make sure that we have the initial stress profile on the ground, and that's basically having our clay material with the boundary conditions that we have defined and the cell weight. So that's stage number one. The second stage is adding the structure. And our structure has been defined on the default mesh set when we have imported the file. We're going to define another stage called backfill, which is basically adding the backfill on the back of the abutment. Another construction stage, which is contraction, because PD 1694 asks you to first apply a contraction and then an expansion. So we are going to add that here. And we are going to make sure that we click on clear displacements, because when we are checking results, we will be only interested on the displacements from this stage onwards. And finally, we apply expansion. We save that, close that, and we have the construction stages assigned. We are almost ready to run this analysis. The only thing that we need to go is go to the analysis tab, in general, and then we set up an analysis case, which is basically the construction stage definition that we have just created. We click on OK. I think it's already defined here. Yes, we have this construction stage. And then, yeah, we click on perform, select the analysis case that we want to run, and click OK. All right, something went wrong for a strange reason. That's why we have backup files. So, yeah, that's the model with the results. Well, after we run the analysis, we will getting results for every single stage that we have created: existing, structure, backfill, contraction, and expansion. The one that we are interested is the expansion one. So we can go here and click on, for instance, if we are interested in seeing the stress profile, the horizontal stress profile, it's going to be this one. And then we'll see this shading color showing how this changes in space, but as well, we can create a cutting line showing the exact profile on the backfill. And we can see the effects of the expansion on the backfill here. Then what we need to do is identify at which depth this stress profile matches the at-rest pressure. And to do that, what I do is I extract that to Excel, this stress profile I'm getting from Midas GTS, which is the blue one, and just identifying when this is the same pressure as assuming at-rest pressure on the abutment. So what I find is this happens at a depth of 5.5 meters. And then I check which is the displacement I'm getting at half this depth, which is basically, this is the displacements I'm getting from Midas GTS again. And then at h divided by 2, I'm getting 6 millimeter displacement. With these two values, h and dd, we can go back to calculating our soil properties. Now, these values have changed from the values we had before. This value has slightly changed, and now we are getting this factor of 14 when before we had 16. That means that we can recalculate now all the Young modulus properties, which are these ones here, and input them in our model and run the analysis again. And if you do that, I'm not going to do that due to time constraints, but if you do that, you will find that in this case, with this second iteration, then the results of Midas GTS is going to yield you something very similar already as this D and H, which means that you have converged and you have your solution for your bridge. So now, since using these updated soil properties, you have the stress profile that you can use for designing your integral bridge. Okay, so that's everything I wanted to cover today. So I guess that now we can go to respond to any questions that you may have. Let's see if I can see any questions. we have. You have mentioned in example 1 the use of model subgrade reaction. Are the springs produced infinitely elastic? How do you ensure compatibility between stress and deformation? Well, they are, infinitely elastic. I understand that there is no yield value. I'm not sure if I'm interpreting the question right. But yes, they are completely elastic because that's how the method of subgrade reaction works. It's just calibration of this parameter for the springs, for linear springs, with some pile tests and some previous experience on site. And then, since they are linear, you will always have compatibility within the stress and deformation. Another one says, in example 1, it has been assumed that the abutment movement can be identified, and how this can be assumed with the presence of piles. And the triangular earth pressure distribution in the 6N assumes pure translation of the abutments, but in reality there will be a rotational interaction with the pile. That's a really good question, because that has been an assumption and we haven't gone to verify that. That's probably what you need to do. Make an assumption initially and see if that's really the case. And this is not always black and white, but I'm going to show you the results of the first example, the movement you get on the back wall. I'm going to change that to millimeters, and hopefully we can see that. So yeah, we have a variation between the values here, from 3 millimeters to 2.5 millimeters. And yes, it's not purely translational in our model. However, by doing that, the first thing is you are ignoring having the V region that's going to act pretty rigid in reality. So you are underestimating the stiffness on this area. And the second thing, assuming that everything moves translational, the case that you're getting is more onerous than a case that assuming that you have some kind of rotation here. So that means that you are on the safe side. So as I said, it's not black and white, but probably making this assumption and seeing that there is not a huge variation between the displacement that you're getting and using the maximum displacement that you're getting on the abutment to extract the K-star, what you're doing is basically assuming an upper bound for the K-star. Another question is, it is possible using Winkler spring multilinear for PY curves and TZ also. So TZ is, instead of using laterally loaded piles, that's for vertical loaded piles, which is commonly used on softwares for pile analysis. And yeah, that can be used. It's just you have to make sure that your nonlinear spring, instead of being aligned on horizontal direction, is aligned on vertical direction, and you define the TZ curve that you want to use. So that's completely possible. Yes. And probably we have time for another question. Let me see. Yeah, there was a question about seismic. We didn't cover seismic. That was outside the scope of this webinar. Another one is how the software will differentiate between pile and structural elements. How does not include interaction properties like normal and tangential behavior for the pile embedded in the ground? And that's another very good question, which I wanted to mention. I forgot when I was discussing. On the second example, we have modeled the pile as fully fixed with the ground, and we know that that's not reality. We can expect to see some differential movements between the ground and the pile. What I've avoided doing in this example, and what you probably need to do when you're doing that yourself, is having an interface element here, which basically represents this friction value that you can expect between the ground and the pile, both on the abutment and also the pile that is embedded on the clay. And what research have findings. What they find is for assessing the K-star and the pressures on the backfill, an upper bound on this friction value is the most onerous one. That's opposite when you're comparing, for instance, retaining structures that, assuming a low value and a lower bound of this friction value, it's going to yield you the most onerous effects. So, and I think, usually you need to use at least 2/3 of the internal friction angle for this interface element. We just didn't have time to cover that on this webinar. Right. I think that's all we have time today. Thank you very much for joining. I think I'm gonna hand back to Jessica.
Okay, thank you, Per, for the presentation, and thank you all for joining today. For the question that we couldn't cover in this session, we will try to get back to you through your email in a few days. And once again, this webinar has been recorded, so the webinar video and the presentation file will be shared. Or you can find all the previous webinar videos from Midas YouTube channel. So if you have any further questions, please contact us to info@midasit.com, or for any users from UK, please contact us to uksupport@midasuser.com. So thank you everyone for today. Thank you.